Okay, so welcome back. Does this work? Yeah. Welcome back from Easter vacation. I'm sure you had a great time. Hopefully doing some revision, I guess. So we're up to lecture 13 here with our course, and so we're going to talk today about rotating reference axes, which are used in several different situations for aerospace engineering. So the types of situations we use these rotating reference frames is when we're trying to model things like rotors, fan turbine blades is another good example, and also things like the Earth space system. So as I mentioned previously, some of this has relevance for sort of more advanced kind of space dynamics. Not that we're going to do anything in this course that gets very advanced, but just to sort of point out your head if you're interested in the future, a lot of this kind of analysis is the foundation for that kind of work. So we're thinking about reference frames and rotation. Then the way we do it usually is we first define a fixed reference frame. And so we normally call those big X and Y. So usually in these kind of reference frame things, there's always something to kind of refer back to as a kind of datum, if you like. So a fixed frame is nearly always given as a sort of reference datum. And then we typically sort of consider points in this reference plane. And then what's usual is we choose one of these points to have a rotating frame going around it because of some specific modeling or application or problem that we want to solve. Okay? So if we've got a couple of points in this reference frame, we call them A and B. Okay, and let's assume that, for example, we want to use point B as a center of rotation. Okay, so we want to define some reference frame . Okay, so we're going to call these coordinates small x and y. And this is rotated with an angle theta. So we've got small x, small y are rotating. So there's several sort of things to set up now, isn't there? If we want to relate big X and Y to small x and y, first thing we need to know is what the distance is of point B from the origin of the fixed frame, isn't it? Okay, so that's a vector here, which we'll call RB. So you notice also that point A is in our rotating frame at the moment, isn't it? Okay, well, it's in the rotating frame the whole time, but it will change. As the thing rotates, point A will change its location in the XY, small xy plane. So we're going to reference A also to the fixed frame as well. So we'll have an RA vector, which tells us where point A is in reference to the fixed frame. And of course, there's a vector between B and A, okay, which we just call R. But just so you know that in our vector notation, this is also equivalent to R A with respect to B, isn't it? Okay. But in a minute, we're going to do lots of differentiating of R, so we'll drop the A with respect to B just to save us having to write it out over and over again. And what we're also going to do is we're going to introduce the vector algebra for the rotating frame. So in the small x direction, we'll have the I vector, okay, and in the y direction, we'll have the j vector, okay, because that's the kind of analytical framework we've been using to study these types of problems. Now, just one other little note about the rotation. So at the moment, as if it's freeze-framed, it's an angle of theta. But if it's a rotating frame, we're assuming it's rotating with a constant angular velocity. Okay, so what we're going to do is just to denote that, we're going to just draw a little arrow there and say that omega, the angular velocity, is equal to theta dot. Okay, so just so that we know that this thing is rotating around with a constant angular velocity, which is equal to omega. And note again that here, this is omega, the scalar quantity, isn't it? Okay, so it hasn't got a bar underneath it, so it's like a scalar quantity. It just means the number. Right? In a minute, when we're going to do some vectors, you'll start seeing omega with the bar underneath, and of course that's a scalar quantity times by the k vector. So k is coming out of the page, isn't it? Do you remember from what we did before? Okay, so it's always worth noting these little subtleties. So what we're going to do to get our analysis going is we're just going to note that we can write down using our vector notation that RA is equal to RB plus R. Okay, so remember what I said, R is RA relative to B, but I don't want to keep writing that down. Okay, so I'm just going to shorten it to R for now. And of course, if you look at the diagram, R is a vector that comes from the origin of the rotating reference frame, doesn't it? Okay. So in fact, we can replace R with the coordinates of the rotating reference frame. So it will be the distance x along in the I direction plus the distance y in the j direction. Okay, and R is in the units of distance, isn't it, or meters. Okay, so we're going to differentiate to get the velocity. So if we differentiate with respect to time, we get RA dot is equal to RB dot plus d by dt of this bracket So to differentiate those things, we've got to use the product rule because I and j are rotating around. They change with time, don't they? But as it happens, they're constant. They change. They're constant functions of time. Okay, so they don't vary, but they do change with time. So we have to, when we differentiate these things, we're going to have to use the product rule. So what do we get? If we differentiate that bracket, we're going to get that same on the left-hand side, RA dot equals RB dot then we get x times di by dt and then y times dj by dt And then the other terms are x dot times I plus y dot times j. Okay, so now in fact we can write this in a slightly neater way, and this is the way it's written in sort of classical mechanics. So the r dots become v, don't they, because r dot is velocity. So we have VA, which just means the velocity of A, it's the same as r dot, is equal to VB. Now, what we're going to write now is that this other bracket here is actually the effect of the rotating axes rotating at a constant speed omega. Okay, so remember that the angle is changing, the rate of change of the angle is omega, and it's a constant. So in fact, we can rewrite this as in a vector notation as the vector omega cross product with r. And I'll talk you through, if you're not sure how that comes about, just pause for a minute and we'll come back to it in a second. And then this term up here, this bracket here, is basically just the velocity of the components in the rotating axis frame. Okay, so we call that V relative. Okay, so we go V underscore subscript REL. Okay, that just means the relative velocity within the frame that's rotating. So let's just make a little note of that. So this piece here so this is the effect of rotating axes. And this term here is the relative velocity in the rotating frame of reference. So let's just have a quick look at that omega cross with r term. Okay, so what I said earlier was that omega the vector is equal to the omega the scalar times the vector k, isn't it? Because that's how we treat rotations of the x and y plane. Okay, and r the vector is equal to xi plus yj. Okay, because that's the x and y coordinates in the rotating frame. Okay, so if you want to do the cross product of those, you'll get the I, j, k. Okay, and so you can actually do this in this way. So if you work out what that is, you'll get minus y omega I plus x omega j. And if you remember from what we did a couple of lectures ago, these omega j and minus omega I are actually derivatives, or they're equivalent to derivatives. So it's actually equal to y times dj by dt plus x di by dt. So, of course, if you look at the way we've written that, we could, if we wanted to, group these two terms together and say that they're equivalent to r dot. Okay, because when we did r dot, it was those two terms, so r dot is these two terms. So this is equivalent on the right hand side to VB plus r dot. So either fortunately or unfortunately, depending on your view, it doesn't stop there, because we actually very often need to know what the accelerations are. Okay, so the accelerations become very important, particularly in things like space systems, because we can relate acceleration to forces, can't we? Okay, so we need to know what the relative acceleration is as well. And of course, what's going to happen is we're going to differentiate the velocity expressions, and because of the product rule, things are going to get more and more complicated, aren't they? Well, that's unfortunately the case, but there's nothing we can do about it. So, if we want to work out what the relative acceleration is, we have to take the time derivative of the velocity expressions. Okay, so we have to do a d by dt of velocity. So on the left hand side it's VA, and on the right hand side we've got d by dt of VB plus omega crossed with r plus V relative. So how do we do that? Well, so what we'll get on the left-hand side, we'll get acceleration, right? So, so we just write acceleration vector A, subscript capital A, and then on the right-hand side, the first term will just be the acceleration at B, so that's just A, acceleration vector B. So then we have to use the differentiation product rule, okay, to deal with this cross-product term. So we'll end up with omega dot crossed with r plus omega crossed with r dot. And then we end up with V relative dot. Okay, well we know from what we did just a minute ago that we know what r dot is. Okay, so r dot is this omega crossed with r plus b relative. So that means we can take this term that's omega crossed with r dot, can't we, and we can work out what it is. So we get
omega crossed with r plus omega crossed with v relative
So we have to, when we're doing these kind of products, we have to leave the brackets in, okay, because strictly speaking we must do that thing inside the brackets first before we then do the additional cross product, so that's why that's left like that. What else have we got? So we've got v relative dot. So that's equal to d by dt of x dot I plus y dot j. Okay, so again we have to use the cross product rule, the product rule when we're differentiating. So we get x dot, well, you could probably work it out, we get something similar to what we had before. And you can see the pattern is emerging, so that first term is essentially a rotational term, isn't it? So that will be omega crossed product with something, and in fact in this case it's omega cross product with a v relative. And then this second term is the relative acceleration, so we call that a relative or a rel. Students really like this derivation normally, kind of sort of thing they do at home for fun after they've seen it. But it is important because you can't send people to the to Mars or whatever without knowing this kind of stuff. Elon Musk does this in his lunch break. So we're going to put that all together now. So what do we get? The acceleration at A is equal to the acceleration at B plus omega dot r, omega dot crossed with r, plus omega crossed with r, plus 2 times omega crossed with v rel, plus a rel. Okay, so it's a bit of a long-winded expression, isn't it? But strictly speaking, if you want to work out what the acceleration is in this rotating reference frame, then this is the type of equation you need. So what are all these terms? Okay, in terms of the physics. Okay, so you may have seen some of these before. So we know that this one's the relative acceleration. Okay, so ACC superscript n is acceleration. Okay, so this term here is the Coriolis. Okay, so that's the Coriolis term, and in a minute I'll try and explain what that is if you don't know already.
This is the centripetal term. This is the angular acceleration. And this, of course, is the acceleration at B. Okay, so relating the two together. So the centripetal force, again, I'm sure you guys have seen most of this before, but we've got something rotating with angular velocity omega. Okay, going around in a circular motion. So if this body has some mass, then the centripetal force is the force pointing back towards the center of the rotation. Okay? Okay, so that's the centripetal. What about the Coriolis? Well, one way to try and explain that is to think about a so if you think about a rotating disc, okay, so if we've got a rotating disc rotating with omega, and somebody is standing on the edge of the disc with a football, okay? So they throw the football towards the center, okay? So they throw the football towards the center point. Okay, so if we start at A, okay, the point when they throw the ball's just leaving their hands, okay, on the edge of the disc. Okay, so then what happens is that the ball is flying through the air, okay, in a straight line towards the center. Okay, so at point B, the ball's got some distance towards the center of the disc, hasn't it? Okay, but the person standing on the edge has actually moved around a bit. Okay, so the person, so that's down the top of their head. Okay, so if they've got a haircut like me, it'd look like that, essentially, from above. Okay, so at point B, the ball is in that vertical line, but they've actually moved slightly round. Okay, then at another point C, okay, ball's there, and they've moved around a bit further, so they're there. Okay? So if we draw the disc again, but now this time we draw what it looks like from the person's point of view, okay, then what you can see is that initially, obviously, there's a straight line through here, okay, but then at point B, so at point A they see that, okay, but at point B they see the ball off to the side, okay, so it looks like the ball's over there, here's the center, and at point C it looks to them like the ball's over there. Okay, so as far as they're concerned, the ball is actually doing this, a curved motion kind of thing. But in the real physics, the ball's going in a straight line, isn't it? Okay, but they're, from their viewpoint, because they're on a rotating reference frame, because they're standing on the edge of the disc, so there appears to be this force which is pushing the ball out and then back in again. Okay, so that's the Coriolis effect, or the Coriolis force. And essentially, it's a product. In this case, it's a product of having a rotating reference frame and the perception of how we see it in that frame. So let's do an example. don't think that's probably okay. So we're going to do an example now. Okay, so let's start. So in this example, what we're going to do is look at this this particular problem. So we've got a disc like this, and it's got like a slot through the middle of it. Okay, so the disc has a slot, and there's a thing inside which can slide freely up and down the slot. Okay, so there's this little thing, we're going to call this the slider. Okay, and what we're going to say is that the origin is O. This slider is at point A. Okay, so it can slide up and down along this. So it can slide up and down along that axis. Okay.
So the point about rotating reference frames normally is what you think, why on earth do I need to know about them? Well, what you can do in certain problems is you can choose them to simplify the problem. Okay? So hopefully you can see in this problem, if we choose the x and y axes to be where those dotted lines are, it'll make our life a lot easier. Okay? Because the slider going along that slot, if we align x with that, then it's always going along the x-axis, makes it easier, and then y is at 90 degrees coming out from the origin. Okay, so we have the y-axis out here, so that's equivalent to our j-axis, isn't it? And we have the x-axis going there, which is the equivalent to our y-axis. Okay, so this example is called motion of a slider. Inside a disc. Okay, so the disc rotates about O. Which is the origin. And we're given some more information as well. So we're given the angular velocity, omega, which is 4 radians per second. And we're given the angular acceleration, omega dot, is equal to 10 radians per second squared. Okay, so they can be in different directions, can't they? The velocity and the acceleration can be acting in a different direction. And in fact, if they're acting in a different direction, it means that it's decelerating or it's slowing down. Okay? And we're given the following information about the slider. So the slider is assumed to be at a distance r from the origin. And we're told that r is equal to 0.15 meters. And then r dot is equal to 0.125 meters per second. And r double dot, the acceleration of the slider, is equal to 2.025 meters per second squared. And they're all given as scalar quantities, all right, so they don't have the lines underneath them, because up to now we haven't really defined the vectors, we're just defining the problem and where the axes lay. Okay? Of course, we can turn them into vectors by multiplying those scalar quantities by I, j, and k as appropriate, can't we? Okay, but for now they're given as scalar values. So the question asks you to find absolute velocity and acceleration
of the slider at A. Okay, so that's what we've got to do. So the first thing we did was we assumed that the XY axes are rotating with the disk. Okay, and because R is along the x-axis, so the slider can only go up and down the x-axis, then that helps simplify solving the problem of finding its absolute velocity and acceleration, okay? So, based on what we've just derived, the expressions we just derived, we know that the velocity at A is equal to VB plus omega crossed with R plus V relative okay, so we can choose where the axes are, okay, on this problem, so we can assume that RB is 0. We can assume that. So if we wanted to define our global reference frame, what we can do is we can put the rotating one and the global one together. So RB can be 0. That gets rid of another term that we don't have to worry about. Okay, and of course that means that our VB is 0 and so on, yeah? So what we get is that VA is just equal to omega crossed with R plus V relative. So how are we going to do that? We need to use the quantities we're given and turn them into vectors. Okay, so what we do is omega the vector is equal to 4 radians per second times k, isn't it? Okay, so to get omega the vector, we take the scalar value, which is 4 radians per second. We multiply it by the k vector. Okay, and then we do the cross product with r. Well, we know the scalar value of r is 0.15 meters. Okay, and it's in the I direction. Okay, so we get that. And we also know that the relative velocity, because that's given to us in the question, is 0.125 meters per second. Okay, so we get that straight away, 0.125, and that's also in the I direction. Okay, so if we work that out, what we get is 0.6 J plus 0.125 I, and for units that's meters per second. So the acceleration term obviously has got more terms in it, so there's more work to kind of to find out what the solution is. But let's start with our expression. So we had acceleration at point A, and what we derived is acceleration at B, but we know that that's basically 0, don't we? Plus omega dot crossed with R plus omega crossed with a bracket of omega crossed R plus 2 omega crossed with V relative plus A relative. So in this example, we're given omega dot in the question, aren't we? So we just go back to the question for a moment. We're told that the scalar value of omega dot is 10 rads per second in the opposite direction from omega, okay? And in fact, of course, that direction is the minus direction, isn't it, in our sign convention for angle? Okay, so what we'll get here when we start to work out what omega dot is crossed with r is we'll have minus 10. Okay, so that's representing that we know that the scalar value of it is 10. Okay, we know it's going in the other direction from in the negative direction for an angle, so we make a minus. Okay, we have to multiply by k. Okay, so this is all to get omega dot, the vector of omega dot, yeah? So this minus 10k, and then we cross that with r. And of course r is relatively easy because that's 0.15 times the I vector. And if we multiply that out, what we get is minus 1.5 times j. So next term we've got to work out is the centripetal term, isn't it? So we've got okay, so we've got this type of expression, haven't we? So we know that omega is 4k, and we've got to cross that with 4k again. Oops, sorry, 4k crossed with r, which is 0.15 I. Sorry, that should be I. And if we multiply that out, we get minus 2.4 times I. Then we've got the Coriolis term, which is 2 omega crossed with V relative. So that's 2 times 4k in bracket crossed with 0.125 times I. Multiply all that out, and what we get is 1 times j. And we're given in the question that A relative is equal to 2.025 I. So then you can plug all of those bits into the expression for the acceleration and come out with you add up the I direction parts and you add up the J direction parts, and so what you get finally, the acceleration at A is equal to minus 0.375 I minus 0.5 J. I'm not forgetting that we need units as well. Okay, it's quite often easy to forget, especially in an exam. You're doing so many I's and J's, you forget that actually acceleration has units as well. Okay, so it asked us to find the acceleration, which is this part, and the velocity, which was this part here. Okay. What you'll notice is that there was some simplifying factors, wasn't there? So because we were able to choose where the axes went, we could eliminate AB and VB, okay? And that simplified the problem. It also told us what some of the things were, and because R was only ever along the x-axis, it made all those cross products nice and easy to work out. Okay, that's it for now. I'll see you on Wednesday.